Here are solutions to homework set number 9 for ECE 463-663 Modern Controls. This homework set looks at calculus variations, the Riccati equation, and full state feedback design using LQG methods. Now the first problem deals with calculus variations. Find the shape of a soap film. A soap film minimizes the surface area, which is this functional, subject to the constraint that the left endpoint is at 8 and the right endpoint is at 7. So here's the shape of the soap film. Here's 0.5708. Now, from the lecture notes, the shape of a soap film is a hyperbolic cosine. This gives you two unknowns. I need to solve two equations for two unknowns. At the left endpoint, when x equals 0, y is 8. At the right endpoint, when x is 5, y is 7. So here's your two equations, two unknowns. To solve, that's where MATLAB comes in handy. There's a function called fminsearch, and that will find the minimum of a function. So if here's your function, I'm going to pass two parameters. That's my a and b. Here's my first equation, second equation, return the sum squared error, and try to minimize that. Now to solve that, I could use trial and error. That is SOAP of, spelled correctly, SOAP of 1, 2. If that's my guess for A and B, there's the shape, and that's the sum squared error. Try different numbers, try and drive it to 0, or let MATLAB guess for you. I'll minimize this function with that initial guess. And in my function, I redraw the soap film every time I iterate. Kind of fun, slows it down, kind of fun to watch. There's one solution. There's actually two solutions. One's a minimum, one's a maximum. There's the second solution. And here's A and B. So either one works. One's a minimum, one's a maximum. The actual shape is the top one. The bottom one is unstable, being a maximum. This is what the shape of the soap film is. Problem 2. Suppose instead I have a soap film. The left side is at 8, the right side is at 3, or I take a mirror right next to it. I pull the mirror out to 3. What is the shape of the soap film when I get to 3? Well, again, from the lecture notes, the shape of a soap film is hyperbolic cosine. At the left endpoint, I plug it in here. At the right endpoint, the derivative is 0, which is hyperbolic sine. I now have two equations, two unknowns. So in that case, here's my first equation, here's the second equation, guess A and B, and keep guessing until the error is 0. In MATLAB, I can do that. Minimize this function. And winds up, here's A, and there's B. And there's the shape of the soap film. And that's one solution. A second solution same one is right here. That's actually the shape of the soap film, the one that goes all the way down. That one will snap. That'd be maximum. This is the stable one. That's minimum. Problem 3. Find the shape of a hanging chain. So what a chain does is it minimizes the potential energy. What shape minimizes the potential energy, which is this functional, subject to the constraint that the length is 15 meters. Excuse me. This is a Lagrange multiplier times length. So here's the total functional. That's the functional for shape of a chain. Again, the solution, go through the lecture notes, get through the solution using the Euler-LaGrange equations. The solutions of this form, subject to the constraint that the length is 15, I can solve that using MATLAB. So again, I've got my first equation, second equation, third equation. I'm going to guess A, B, and M. and return the sum squared error. So again, what I can do is in MATLAB, I could do guess is A, B, M, 1, 2, 3. There's the shape, there's the sum squared error, saying, nope, not even close. Or I can use fmin search. It'll sit there and iterate when it finds the shape, kicks out the answer. Here's A, B, M. There's the shape of the hanging chain with a length of 15. What's kind of neat about that is I can say, let's make the length 11. Repeat. There's the shape with a length of 11. Can hyperbolic cosine. Make the shape 22. There's the chain with the length of 22. So with calculus variations, there's a couple things you can calculate. Soap films, hanging chains, anything else gets just way too hard. A couple other problems you can solve though. This is getting more towards feedback control. Suppose I want to build or go from point A to point B. Point A is at 0.8. Point B is at 10.7. I want to go to point A to point B. I want to minimize, this is time and x, minimize x dot, the slope, and x squared. X dot squared, 10x dot squared, and x squared. The approach then is, here's my functional. Any solution has to satisfy the Euler-LaGrange equation. That'd be the partial with respect to x minus the full derivative of the partial with respect to x dot is 0. Partial with respect to x is 2x. Partial with respect to x dot is 20x dot. Take the full derivative. Use the Laplace operator that says either x equals 0 or s is plus or minus 0.3162. Using the latter solution, here's the form of x. Plugging in the two endpoints, at the left endpoint, when x is 0, y is 8. When x is 10, when t is 10, x is 7. Two equations, two unknowns, solve. And here's your equation. That is the optimal path going between point A and point B. And what that looks like is this. Here's point A. Here's point B. This path minimizes x squared plus 10x dot squared. Next problem. This is when we're getting into feedback control. Here's a first-order dynamic system. I want to minimize this cost function. Subject to the constraint, I go from 8 at t equals 0 to 7 at t equals 10. So what's the optimal path going from point A to point B for this dynamic system with that cost function? My functional will be my original one plus the Lagrange multiplier times my constraint. I've got three variables, x, u, and m, gives me three Euler-Lagrange equations. Here's the first one, second one, third one. Now to solve, a couple ways to solve. What I'm going to do is solve for u in terms of m and substitute. Solve for m in terms of m, x, and x dot. Substitute. And I wind up with an equation just in x. So x has to satisfy this differential equation using Laplace operator. Either x equals 0 or s is plus minus 0.59. Going with the latter solution, here's the form of x. Plug in the endpoints, and you wind up with a is 0.01, b is 7.98. And here's the path, going from A to B. If you want to know what the input is, I can just plug it into this equation. Once I know x of t, where was it? I know x of t, I know what x dot of t is, solve for u. The last ones. Now design a feedback controller for a cart and pendulum system. So here's one way to do it. I have the dynamics for the cart, my ABCD matrix. Here's my desired response. That gives me the red system. Maybe give a little bit more overshoot. I will then specify Q and R. So my states are position, angle, velocity, angular velocity. I want to make the actual step response, the blue line, look like the red one. So these are the knobs. If I crank up the gain on position, it should get faster and faster. Yeah, looking pretty good. That's actually pretty good. Once I wind up with my gain, here's position, angle, velocity, angular velocity. I play around with velocity. That's what it does. Kind of subjective. Come up with a response that looks good. There's extra delay in the system, so I'm going to plot the desired step response with a delay. That may be too much. That looks really, really good. Okay, so really I'm just playing around with Q. There's really no magical value for those numbers, just whatever seems to work. Once I'm happy, I've got my Q and R. What that tells me is here's my feedback gain, Kx and Kr. Here's the optimal place to put the poles. Using pole placement, I could do something similar, like let's say minus 0.8 plus j minus 0.8 minus j minus 4 minus 5. So to do that, here's the feedback gains using pole placement. Here's the feedback gains using LQR. And they actually look pretty darn similar. The pole location with pole placement is where you put them. Minus 0.8 plus minus j, minus 4 minus 5. Here's what it is with LQR, which is actually just about the same. It's kind of dumb luck. Different ways of finding the gains. With pole placement, the fast poles, I really don't know where to put them. So if I chose here, I'd wind up with much, much higher gains. Doesn't really change the response. The problem with pole placement is I don't know where to put the non-dominant poles. That's an advantage of LQR methods. All the poles drop out. And you get a decent response. That's really the design approach with LQR. Just use Q as a knob to play with the knobs, play with the gains until the response looks good. That's for a cart and pendulum system. Going to the next problem. Design a feedback controller for ball and beam system using LQR methods. Again, the procedure is pretty similar. I just use Q and R as knobs to play with. If I say Q, weights position, position, angle, velocity, angular velocity, just weight position, it doesn't look real good. Let's weight angle. Doesn't really seem to help. Velocity, help a little bit. Angular velocity, not as much. Let's weight the one that seems to work. So crank up the gain, try to get rid of the oscillations. That's actually not too bad. That's about 10% overshoot. Maybe that looks good. Kind of subjective. When does it look close? Oh. I lost a term. Too much. Keep playing with the numbers until it looks close enough. Once you're happy with Q and R, again, nothing magical about Q, it's whatever it takes to give me the response that I want. When you're done, Here's my feedback gain kx. Here's the optimal place to place the closed loop poles. Again, nothing magical about that. That's just kind of where they go. What's nice about LQR is you tend to get better feedback gains. If we were to do pole placement, getting a similar response, I wouldn't know really where to put the poles. They say, put the closed loop poles there. I would get, maybe higher gains. Put poles at -6, -7. Again, with pole placement, I don't really know where to put the non-dominant poles. They don't really affect the response, but they do affect the feedback gains. Advantage of LQR methods is you get a decent response, but you tend to get smaller gains because I'm weighting the input squared. So here's the feedback gains, and there's my step response shown in blue. So LQR is really just another way of finding feedback gains. You've got pole placement, that works. You've got LQR, that works. They're just knobs, just tools. Whichever tool works for you, use it. So there's another tool to play with, LQR. And that's homework set number 9 for 463.